Hello everyone, welcome to the course Nature and Properties of Materials. In week 4, we'll talk about polymers. So this course is offered by Professor Vishak Bhattacharya from Department of Mechanical Engineering, IIT Kanpur. I'm your TA, Alka Jangid from IIT Kanpur. So firstly, we'll be going through some sample assignment questions which will be helping you in solving your assignments. Okay. Then we'll go through some lecture notes. So first, we'll go through questions related to your assignments. Okay, so first question is, which one of the following types of the molecular structure present in the thermosetting polymers? Your options are linear polymer, branched polymer, cross-linked polymer, or network polymers. So the correct answer here will be cross-linked polymers. So in case of thermosetting polymers, they are highly cross-linked, which makes them they can be made into some shape only once, and after reheating them again they won't be taking another shape. Okay, they directly burn. So that's why these are the thermosetting polymers which are highly cross-linked polymers. Now next is explanation. So here you can see these are the linear types of polymers which are thermoplastic, and then we have cross-linked polymers which are thermoset. So in case of thermoset, there will be covalent bonds forming them. And so in case of thermosetting polymers, they are highly cross-linked. And a thermosetting polymer, often called a thermoset, is a polymer that is obtained by irreversible hardening, curing a softening solid or viscous liquid pre-polymer, which is known as resin. And this process is known as curing. Okay, so also these are the structures that will be for linear polymers and thermoplastics, and this one will be the cross-linked polymers for thermosets. Next question is, which one of the following is an example of thermoplastic material? Your options are camera bodies, electric installation, or electric plugs, automobile parts. So correct answer here will be electric installation. So other than that, all the options, they require to be highly rigid bodies. So that's why these are all made with help of thermoset uh, plastics. Okay, so here we can see that in bakelite and other resin, thermosets are used for making electrical plugs. And automobile parts and camera bodies also need to be very rigid and high temperature sustaining. So these are also made of thermosets. Next question is, which one of the following monomers can be used to create a polymer through addition polymerization? Your options are ethylene, polypropylene, styrene, or all of the above. So as you know, all of these monomers are used in making polymers. So such as polyethylene, polypropylene, polystyrene. All these are used widely in making some of the plastic applications. So correct answer here will be all of the above. And explanation here will be, addition polymers are formed when monomers bond to each other without the loss of any other atoms. Examples of addition polymers include polyethylene, which is made from ethylene monomers, and it is used for packaging films, toys, bottles, coatings, and etc. Next is polypropylene, which is made from propylene monomers, which is used for hinges, molding, rope, outdoor carpeting, etc. In case of polystyrene, it is made from styrene monomer, and it is used for transparent containers, foam cups, insulation, etc. Next is polyvinyl chloride, also known as PVC. It is made from vinyl chloride monomers used for pipe and tubing, raincoats, photographs, records, and etc. Next question is chain polymerization mechanisms may occur due to. Your options are free radical, cationic, anionic, or all of the given options. So in case of chain polymerization, these all three are the mechanisms which can be used. Okay, so all of the given option will be the correct answer here. So, in explanation, free radical polymerization is a type of chain growth polymerization along with anionic, cationic, and coordination polymerization. And free radical polymerization is a polymerizing approach by which successive addition of free radicals takes place to form a polymer unit. Next question is, if a sample of polystyrene has a molecular weight of 100,000 gram per mole and each repeating unit has a molecular weight of 104 gram per mole, then what is the and question is, what is the degree of polymerization of the polystyrene sample? Your options are 960, 9,600, 10,000 or 100,000. Okay, so correct answer here will be 960. So for this you need to remember the formula for degree of polymerization. So it is defined as the number of repeating units in a polymer chain. So dp can be given as mn bar divided by m. So mn bar is number average molecular weight. Okay, and small m is the repeat unit molecular weight. So here number of atoms is here small m is the repeat unit molecular weight, number of atoms times the atomic weight. So 104 gram per mole will be for the polystyrene, and number average molecular weight is already given 100,000 gram per mole. So here you have to just divide 100,000 with the 104 and you'll be getting the correct answer as the degree of polymerization as the 961.53. So the nearest to this is 960. So first one will be the correct answer. So degree of polymerization will be, so how many units are in a particular polymer chain. So higher this one degree of polymerization will be, higher the uh, monomers will be in a single chain. Next question is, a polymerization reaction with 10 monomer units produces a polymer with a molecular weight of 1000 gram per mole. So what is the degree of polymerization? So it is similar to previous question. Okay, so here also you have to just divide 1000 with the 10 monomer units and you'll be getting okay, so you'll be getting 100 as the correct answer. So 100 will be correct answer here, not 10. Okay, so in explanation, you can see the degree of polymerization is defined as the number of repeating units in a polymer chain. To shift this more. Okay, so 100 will be the correct answer. Here the degree of polymerization dp is defined as the number of repeating units in a polymer chain. So dp can be given as mn upon m. Mn will be number average molecular weight, m will be repeat unit molecular weight. So number of atoms times the atomic weight. And dp again can be given as the 1000 molecular weight divided by number of monomer units. So 10. So it will be 100 will be the correct option here. Seventh question is the characteristics of condensation polymerization are given below. So here you have to find which statements are correct. Okay, so here first statement is only CC linkages present in the polymer structure. Second option is use of bifunctional or polyfunctional monomers. And third will be the elimination of a small byproduct molecule. So here one of the option is incorrect. So which one is the first one? Because in case of condensation polymerization you can have other atoms such as oxygen and nitrogen as well. So 2 and third will be the correct options. And so besides CC linkages, polymer structures also contain atoms such as oxygen, nitrogen, etc. at regular intervals in the main chain. So here also you can see in case of nylon, you have nitrogen in the main chain. Okay. Which of the following polymer type is not classified on the basis of its application and properties? Your options are rubbers, plastics, fibers and synthetics. So the correct answer here will be synthetic. Okay, so synthetic is dependent on classified on the basis of origin. So it can be either synthetic or natural polymers. Okay, and rubber, plastic and fiber, it is depending on the application, final use and properties. Okay, so there are two types of polymers, synthetic and natural. And synthetic polymers are derived from petroleum, oil and made by scientists and engineers. Examples of synthetic polymers include nylon, polyethylene, polyester, Teflon and epoxy. And the natural polymers, they occur in nature and can be extracted. So synthetic polymers are classified on the basis of their origin and are known as man-made polymers and natural polymers. Okay, the classification is into that, and synthetic is also known as man-made polymers. Next question is which of the following is a thermosetting polymer? Your options are polystyrene, polyolefins, polyolefins and nylons and phenolic resins. So your correct option here will be phenolic resins, which are uh, phenolic resin is the only one that is thermoset. Other than that, all these are thermoplastics. So phenolic resins fall under the clan of the thermosetting polymers, and the rest are the thermoplastic polymers which can be softened repeatedly on the application of heat. Now next question is polystyrene is a blank polymer. So your options are linear, branched, cross-linked and network. So in case of polystyrene, it is a linear type of structure. Next question is which polymer is an example of branched polymer? So you can think of this question as in if you are making more branches of your polymer chain, then it is more likely to withhold that particular gap between two chains. So this gap will be reducing the density of entire polymer. That's why the correct answer here will be low density polyethylene. The polyurethane, nylon and high density polyethylene, these all are linear type of chains. Next question is which one is a characteristic of a thermoset polymer? Your options are ductile, non-post formable, creep prone and recyclable. So here in case of thermoset polymer, they are brittle compared to the thermoplastics, and they are also not prone to creep. They withstand temperature, higher temperatures compared to thermoplastics. And they are not recyclable as well, because if you set the plastic ones, then it will be retaining only that shape, and if you again reheat it, it's more likely to burn rather than shaping into another shape. Okay, so that's why these are the only correct option for this is non post formable. Next question is, which statement is incorrect? Your options are: cross-linking restricts the molecular motion, cross-linking makes polymer insoluble, cross-linking reduces chain mobility, and cross-linking reduces glass transition temperature. So the correct answer here will be cross-linking reduces glass transition temperature. So as you keep on increasing the cross linking, it will make your material more brittle, so it will lead to increase in the glass transition temperature, because below glass transition temperature your material is glassy, meaning brittle, and above that it is plastic. Okay, so it will behave more like more flexible above that particular temperature. So if glass transition temperature is increasing, then there will be more temperature range in which your material will behave as brittle material. So cross-linking leads to that particular brittleness. And other options such as cross-linking restricts the molecular motion, and cross-linking makes polymer insoluble, cross-linking reduces chain mobility. These all are correct. Okay, so I told it incorrectly. So which statement is incorrect? So only this statement is incorrect and others are correct. Okay, so cross-linking will be reducing your chain mobility. It will be making your polymer more insoluble, and it will be restricting molecular motion. And cross-linking will increase glass transition temperature. Okay, so I told this one as well. So why it will be increasing? Because it will be enhancing the range in which your polymer will be reacting as brittle material. So that will be the incorrect option. What is the increased in a material on the addition of plasticizer? So as the name suggests, your plasticizers will be increasing plasticity in material, plasticity and fluidity. Other things will be reducing. So hardness is reduced. Plasticizers basically introduced in materials which are rather brittle. So to make them more tough, you add plasticizers. Okay, so after adding these plasticizers, your material will be acting more plastically, and it will be showing higher fluidity. But the glass transition temperature, it will be reducing, because your material is becoming more plastic. So the range of the above region will be increasing. So your glass transition temperature will be depressed. And the hardness will also be reducing, because your material is becoming more tough. Okay, and it's becoming more plastic. And stiffness will also again reducing. Okay, now we'll go through some lecture notes. Okay. Okay, so now we'll be going through lecture assignment notes. Okay, these one will be helping you in solving your assignments. So firstly, the foremost thing is the what are polymers and what are their main classifications. So firstly, polymers are just hydrocarbon chains in which you can also have oxygen, nitrogen, fluorine and some other atoms along with hydrocarbon, but the chain mainly will be manufactured by hydrogen and carbon. Okay, so these materials will be having long chains, and the chains will be along the chain you will be having covalent bond, and in between two chains you can have different types of bonding such as hydrogen bonding or weaker van der Waals bonds as well. Next is firstly based on molecular structure. So the classification based on this, so your structure can be linear, it can be branched, it can be cross-linked, it can be of network type of uh, structure as well. Okay, so these type of structures are given here. Okay, so these are the linear type of structure. Linear, so the your hydrocarbon chains are in linear structures, so there will be long chains forming. Then you have branch type of structure, so you will be having some branches that will be forming along the other direction compared to the main chain. Then you have cross-linked, so there will be cross-linking in between two chains with the help of covalent bonding. Then you also have network type of structure which will be forming this. You must have seen silica structure in previous lectures, so this type of structure will be forming. 3D type of network will be forming, making it insoluble and infusible. So based on molecular structure, you have these four classifications. Then based on origin, so how you receive your polymer, based on that also you have these classifications: natural and synthetic. So if you're getting your polymer directly from nature, then it will be natural type of polymer. If it is man-made, then it is synthetic type of polymer. So polyethylene, polystyrene, all these are synthetic, and natural will be such as natural rubber, these cotton and other type of these polymers. Next is based on polymerization reaction. So based on this, again you have two types of polymers having either chain polymerization or step polymerization. Then based on thermophysical behavior, so if you're providing heat to your particular polymer, how it will behave. So if it's easily can be formed into another shape, then it will be thermoplastic. And if it can be given shape only once, and after if you reheat it, it will burn, then it will be thermoset. Next is based on end use of applications. So based on that you have these many types. So it can be either plastic, elastomer. Elastomer will be having a lot of elasticity and will be highly ductile. Fibers. Fibers will be having a higher L by D ratio, length upon diameter ratio. Coatings. So you can be having these polymer coatings as well. These are mainly used for providing some corrosion resistance. Adhesives. Adhesive can be also one of the application of polymers. Then you can have films and foams. Foams will be having highly porous structures. Then you have advanced polymers, which can be ultra high molecular weight polyethylene or liquid crystal polymers. Now, polymers classification based on origin. So first is polymer is a large molecule composed of many repeated subunits. So the word polymer, it is made with the poly and mer. So poly meaning many, and MER, this stands for various parts and units. So a lot of parts combined will be forming your polymer. So next is type based on origin. First will be natural polymers, which will be consisting of cotton, silk, natural rubber, proteins, cellulose, starch, bone, leather, etc. In case of synthetic polymers, you have synthetic rubber such as neoprene, bakelite, neoprene, nylon, polystyrene, polyethylene, polyvinyl chloride, etc. And these are some of the applications of polymers in making these bottles, tires, and snooker bowls, these forks and spoons, and these cycle helmets. Next is classification based on molecular structure. So firstly we have linear type of structures. So in this case, you have units which are joined together end to end in single chains. And these may be some weak van der Waals and hydrogen bonding between the chains, and along the chain you'll be having covalent type of bonding. And these are soluble and fusible in various solvents, and examples include high density polyethylene. So because these have linear type of structure, they can come close together compared to this type of structure. So these branches and these cross links reduce the density of these polymers. So high density will be in case of linear type of structure. Okay, so other is PVC, polyvinyl chloride, also polystyrene, nylon, polymethyl methacrylate. In case of branched, you have side branch chains which are connected to the main ones. These are more soluble and fusible, and examples include low density polyethylene. Next type is cross-linked. So it is adjacent linear chains which are joined one to other at various positions by covalent bonding, and these are insoluble and infusible. And next is network type of polymers. So these have high cross linking and 3D type of network, and these are insoluble and infusible. Examples include rubber, polyurethanes, and phenol formaldehyde. Next is classification based on thermophysical properties. First we have thermoplastics. So in this case, you have materials which are heat sensitive. So these soften and flow upon heating. These remain soluble and fusible under many cycles of heating and cooling. Thus, they are recyclable. Next is most linear polymers, and those having some branch structures with flexible chains are thermoplastics. And the individual polymer molecules are held together by weak secondary forces such as van der Waals forces, hydrogen bonds, dipole-dipole interaction, and these bonds, they are easy to repair by welding. These thermoplastics, they can be easily repaired by welding or solvent bonding, etc. And these have unlimited shelf life as they won't undergo polymerization during storage or in processing unit. One of the disadvantage that these are prone to creep, so they can be used at higher surface temperatures. And examples include polyethylene, polystyrene, polyethylene, polyethylene terephthalate, polyvinyl chloride, nylon, polypropylene, polymethyl methacrylate. Oh, wait. Okay, so next we have thermoset plastics. So in case of thermostatic polymers, these are the network polymers, and these are also creep resistant, and these are less sensitive to temperature, and these attain permanent hardness due to cross linking and then do not soften and flow upon heating. They do not soften or flow upon heating. So these materials are used at higher temperatures compared to thermoplastics, not very high temperatures, because polymers, they can be used above like say 500 600 degrees Celsius, and but compared to thermoplastics they can be used up to higher temperatures. And these are non-post formable, so these are obtained in a soluble or fusible stage in the early or intermediate stage, but once they get cured they will be infusible and insoluble, and they have excellent thermal and chemically stable once polymerized, and the disadvantage include brittle and non-recyclable. And the other example include bakelite, epoxy and urethane, etc. So the excellent thermal and chemical stability once polymerized. So compared to thermoplastics and even metals, they show higher chemical stability. And thermal stability is poor compared to metals but better compared to thermoplastics. These are also brittle compared to thermoplastics. Thermoplastics show higher ductility compared to thermosets, and also these are non-recyclable. Next is curing of the thermosets. So curing is the process to transform thermoset resin, which is soft, solid or viscous state, into an infusible, insoluble polymer network under heat and pressure. Viscosity of the system rises until gelation occurs. And at this point, two phases exist, a gel phase and a sol phase. Okay, in which the gel phase is the gelled part and the sol phase can be extracted with solvents. The amount of sol phase present decreases as the reaction progresses further, and upon further reaction, vitrification, meaning hardening, occurs. So here in the diagram also you can see, firstly you have some monomers which in liquid state, so as we keep on moving further the viscosity will increase. You'll be having two different phases, gel and sol. Then after that there will be formation of glassy structure, which is the vitrification or hardening process. Next is addition polymerization reaction. So in this case monomer units are attached one at a time in a chain like fashion to form a linear macromolecules. So here these are characterized by the presence of a few active sites which react and propagate through a sea of monomers used for the synthesis of thermoplastics. So firstly you have initiator decomposition. So the catalyst will get divided into two radicals, 2R star. Now this radical will combine with the monomer and create this chain reaction. Okay, so chain initiation will begin, R star plus M. So here you will be having RM1 star. Then you have chain propagation. So this Rm star will combine with another monomer and this will keep on increasing, and you'll be getting these uh, these high length chains, and these chains will again finally combining and terminating these radicals, and these radicals will be going out of the chain and you'll be getting these polymers. Next is condensation polymerization reaction. In this case, you don't require uh, any radicals. So it involves more than one monomer species, and the monomers can react with any nearby monomer. And here no special activation is needed to allow a monomer to react. And here a small molecular weight byproduct such as water that is eliminated or condensed is formed. Okay, here typical reaction is shown. So in first step, you'll be having two monomers coming together and forming one of the uh, one of the part, and then you'll be getting some byproduct. Okay, so small molecular weight byproducts such as H2O or ammonia, these are formed. Second step, you're getting this chain will again keep on reacting with the other monomers and will be keep on moving further. So this is the final reaction, how it can be written. So Mn, MM, then it will be forming M plus N plus H2O. The thermosetting polyesters, phenol formaldehyde, nylons and the polycarbonates are produced by condensation polymerization. Next we have advanced polymers. One of the examples include ultra high molecular weight polyethylene. So in this case, linear polyethylene that has an extremely high molecular weight, 4 times 106 gram per mole, and its trade name is given as Spectra or Dyneema. It is an extremely high impact resistance, and it also has outstanding resistance to wear and abrasion, and it has a very low coefficient of friction and a self-lubricating and non-stick surface. It has very good chemical resistance to normally encountered solvents, and it has very highly excellent low temperature properties. It also has outstanding sound damping and energy absorption characteristics. Demerit include mechanical properties diminish rapidly with increasing temperature. Okay, so these are some of the applications and their properties. So in case of ultra high molecular weight polyethylene, you'll be having high impact resistance, good resistance to wear and abrasion. That's why they are used in making gears as well. And they have very low coefficient of friction. Again, it is a useful quality for making gears. Self-lubricating and non-stick surfaces. Very good chemical resistance to normally encountered solvents. So store bottles are also can be made out of this, and excellent low temperature properties and sound damping properties and energy absorption characteristics. Next is liquid crystal polymer. So in case of aromatic polyester based on p-hydroxy benzoic acid and related monomers, these are in the liquid crystalline state, being neither purely crystalline nor purely liquid, and it is considered as a new state of matter. It is capable of forming regions of the highly ordered structure while in the liquid phase, but regularity lower than the solid crystal. It is extremely unreactive and inert and highly resistant to fire. It is used in liquid crystal displays on digital watches, flat panel computer monitors and televisions and other digital displays. Next is some of the applications of polymers. So first is in making films, foams, coatings and fibers and adhesives. These are the division based on the applications. and previous one was for the advanced type of polymers. Okay, so in case of films, you have polymeric films which are having thickness between 0.025 to 0.125 mm, which are used extensively as bags for the packaging food products and other textile products. Some of the important properties include low density, high degree of flexibility. So these thin films will be flexible and having low density, and these also have high tensile and tear strength. It also has resistance to moisture and other chemicals, and examples include polyethylene, polypropylene and cellophane type of thin films. In case of foams, you have these contain a relatively high volume percentage of small pores and trapped gas bubbles, and it is commonly used as cushions in automobiles and furniture as well as in packaging and thermal insulation. Next is coatings. So ingredients in coating materials are usually organic polymers which are classified as paint, varnish, enamel, lacquer and shellac. It is applied to the surface of materials to protect the item from corrosive or deteriorative reactions, to provide electrical insulation. So as we know, polymers are basically insulators. So for providing insulation to metal wires, you can provide coating of these polymers, and to improve the object's appearance. Okay, so your wires can undergo corrosion with time, so they can lose the aesthetic. So to improve that, you can provide coating of these polymers which don't corrode and they remain good looking over the time. Next is fibers. So fibers are the long filaments having at least 100 to 1 length to diameter ratios, and these are subjected to mechanical deformations, stretching, twisting, shearing and aberration. And these fibers are widely used in textile industry for being woven into fabric or cloth. Next application is in making adhesives. Now it is used to join a large variety of materials such as metals, ceramics, polymers and composites. Advantages include lighter weight. So compared to metals and ceramics, these are lightweight materials, and its ability to join dissimilar materials and thin components. And it has better fatigue resistance, and it also shows lower manufacturing costs, and some of the limitation include high temperature. So these adhesives, they are polymeric in nature, so you can take that particular component which has the adhesive which is joining two parts to very high temperature, because this adhesive will lose its integrity and the assembly is more likely to fall apart. Next you have natural adhesives, which are animal glue, casein, protein, starch, carbohydrate and rosin, which is from pine tree. Artificial adhesives include epoxy, polyurethanes, cyanoacrylate and acrylic polymers. Applications include aerospace, automobiles, sticky notes, etc. Next is elastomers. So in case of amorphous polymer with viscoelasticity, viscosity and elasticity, very weak intermolecular forces, low Young's modulus and high failure strain, compared with other materials. Okay, so elastomers, they are amorphous polymers with viscoelasticity. So some part will be viscous, some part will be elastic, and these are very weak intermolecular forces, which and also having low Young's modulus and high failure strain compared with other materials. For a polymer to be an elastomer, it must not easily crystallize and the molecular chain should remain naturally coiled in the unstressed state. Okay, so if a material is more likely to crystallize, then it will not act as brittle polymer. And if it is not crystallized and it remains uh, in uncrystallized state, then it will act as viscoelastic material. Okay, and it must not easily crystallize. These molecular chains should remain naturally coiled in the unstressed state, and the chain bond rotations, they must be free to readily respond to an applied force. And it has delayed plastic deformation, and some of the examples include silicon rubber, butyl rubber, nitrile rubber, and polychloroprene and neoprene, etc. Applications include gasket seals, which fill the space between imperfect mating surfaces to prevent leakages, and other applications include noise and vibration dampers and the car door seals, etc. Next is plastics. So these are malleable and these can be molded into solid objects of diverse shapes. Some plastics are very rigid and brittle as shown in curve A. So this curve shows brittle plastics, and others are flexible as curve B. And it is used in general purpose applications, and it may be either thermoplastic or thermosetting as well. So here you can see three types of polymers: elastomers, plastic, and brittle polymer. So these type of curves they will be having. So this material has slope which is very high, so it will be also having high Young's modulus and also high UTS. But you can see fracture strain for this material is very low. So this material is brittle in nature and toughness is also very low. For plastic material, you will be having moderate type of ductility as well as strength. So these are the plastic. Then in elastomers, you have high ductility but very low UTS. And so some plastics, plastics are malleable and can be molded into solid objects of diverse shapes. And some of the plastics are very rigid and brittle as shown as curve A. Others are flexible as curve B, and these are used in general purpose applications as well. Now it may be either thermoplastic or thermosetting type of materials. Next is applications of some polymers. Okay, so your first polymer is polyethylene, and its applications include in making toys, battery casings, bottles, and carry bags. Next is polystyrene, which includes applications such as thermal insulation, packaging, and consumer goods. In case of polyester, you have clothing, robes, bottles, etc. Next is acrylics, which include outdoor signs, lenses, aircraft enclosure. Next is nylon. It is used in making clothing fiber, conveyor belts, fasteners, etc. Polypropylene. It is used in making syringes, petri dish, and plastic furniture. Next is Teflon, which is used in making non-stick pen and Teflon tape and bearing coatings. Epoxies are used in making metal coatings, composites and adhesives. Next is molecular weight. So there are two types of molecular weight. One is number averaged, second is weighted average. In case of number average molecular weight, you have the total weight of all of the polymer molecules in sample, which is then divided by the total number of polymer molecules in a sample. This formula you can see. Then for weighted average molecular weight, it's based on the fact that the bigger molecule contains more of the total mass of the polymer sample than the smaller molecules do. Next is degree of polymerization, dp. So it is given as mn upon m, where mn is given as number average molecular weight, m is repeat unit molecular weight, which can be given as number of atoms times atomic weight. Next is example. So suppose for polyvinyl chloride having Mn, number average molecular weight is 21,150 gram per mole, and then repeat unit molecular weight is M equals to 202 multiplied by 12 plus 3 multiplied by 1 plus 1 multiplied by 35. So 35 is chlorine. So the correct answer will be, so for repeat unit molecular weight you will be having 62 gram per mole. Then degree of polymerization can be calculated based on the initial polyvinyl chloride molecular weight divided by 62. So it will be around 341. So here from this graph also you can see with increasing degree of polymerization, you see that the melting temperature of the polymer is also increasing. So as you keep on increasing degree of polymerization, the number of monomer in the one particular chain. So if you keep on increasing it, your melting temperature of material will also be increasing. Next is polydispersity index. So Pi is given as the uh, divide this molecular weight divided by number average molecular weight. So the larger the polydispersity index, the broader the molecular weight. And the monodisperse polymers where all the chain lengths are equal, such as a protein has Pi equal to 1. So step polymerization reactions typically yield values of 2, and for chain polymerization the reactions yield values between 1.5 and 20. Next is copolymerization. So here when there is more than one type of mer present, the molecule is a copolymer, and the copolymers are commonly type of material which is used commercially. Examples of copolymers are ABS, polyethylene vinyl acetate, and nitrile rubber. The copolymerization is the method by which a copolymer is created from various types of monomers, and it is frequently used to enhance or change particular characteristics of plastics. Some types of copolymers include draft copolymers and block copolymers and alternate copolymers. So in case of graft polymers, you'll be grafting other polymers chains onto the initial A type of polymer. Okay, in case of block, you'll be having these type of blocks of one copolymer and another and the next here attached like this. In case of alternate copolymer, you'll be having AB, AB, AB type of sequence. Random copolymer, there won't be any arrangement. It will be random. Next is physical states of polymers. So firstly, classification of polymer materials. It's partially crystalline state, viscoelastic state, and highly elastic state, which is rubber. Then you also have glassy state, which has organic glasses from polystyrene, polymethyl methacrylate, and polyvinyl chloride. Here also you can see the liquid polymer unit melt after cooling it. It can't undergo perfect crystalline, but it can undergo and form partially crystallized material. Next is crystallinity in polymers. So crystalline region, which is orderly arranged in molecular chains, and the highly crystallinity means higher density, more strength, and higher resistance to both dissolution and softening by heating. The density of crystalline polymers is higher than amorphous polymers due to the close packing. So here also you can see there are crystallized regions in between and which is surrounded by material which is not ordered. So crystalline region surrounded by disordered structure. So the density of crystalline polymers is higher than the amorphous polymers due to close packing. So from here also you can see this one has less atomic packing compared to this one. Now the degree of crystallinity in polymers so ranges from completely amorphous to about 95% crystalline but never 100% crystalline. Now metal specimens are almost always entirely crystalline and the ceramics are either totally crystalline or totally non-crystalline. Next is crystallinity in polymers. So degree of crystallinity is affected by your first is rate of cooling during solidification. So if you are cooling your material very fast, there will be less time for alignment and there will be reduction in crystallinity. Next is chain configuration. More the side branching and cross linking, more will be the restriction to prevent the chain alignment and lesser the crystallinity. Now the most network and cross-linked polymers, they are almost totally amorphous. Crystallinity in polymers. So examples of highly crystalline polymers include polypropylene, nylon and Kevlar and Nomex. Examples of highly amorphous polymers include polymethyl methacrylate, also known as PMMA, polycarbonate and polyisoprene. And this is the formula that is used for calculating percent crystallinity. So here rho C times rho S minus rho A divided by rho S brackets P rho C minus rho A. Rho will be the density, C will be the perfectly crystalline polymer, S is for specimen, and A is for the totally amorphous polymer. Next is tacticity. So tacticity determines how easily your chains can move and how easily your material can be flexible. Okay, so in case of tacticity, it is different atomic configurations for the same composition. So there can be different type of configuration possible. So here you can see this chain is opposite to this previous one. So here you can see this is the another structure compared to this one. So this also different can make your properties different for these materials. So tacticity is the way dependent groups are arranged along the backbone chain of a polymer. Okay, and next is isotactic and syntactic, which is regular geometry facilitates the fitting of the adjacent chains, thus they are more crystalline. Atactic is the poorly crystalline due to irregularity of the side group. Also, larger the side bonded groups of the atoms, lesser will be the tendency for crystallization. Next is glass transition temperature. So here definition. So the temperature at which the polymer experiences the transition from rubbery to rigid states. And below Tg, polymer becomes hard and brittle like glass due to the reduction in motion of the large segments of molecular chains with decreasing temperature. Here Tg is different for each polymer and the glass transition happens only to polymers in the amorphous state. Here also you can see if you are heating and cooling your material, then it should follow one particular path rather than both of these paths. So there is glass transition temperature that is shown here, and then you have supercooled liquid, then you have formation of glass. So in case of metals, you have crystalline solid, then crystallization. Um, from liquid, you'll be going to the supercooled liquid, then you will be forming glass. While in case of metals, you'll be crystallization, then you'll be getting crystalline solid. So here T will be lesser than Tg. Then in that case, your material will act as brittle material. So here also you can see Tg of various materials. So glass transition temperature definition can be given as the temperature at which the polymer experiences the transition from rubbery to rigid states. And below Tg, your polymer becomes hard and brittle like glass due to the reduction in motion of the large segments of the molecular chains with decreasing temperature. And the Tg is different for each polymer. Glass transition happens only to polymers in the amorphous state. Now for polyethylene of low density, you have glass transition temperature of minus 110 degree. And the melting temperature is 115 degrees Celsius. For polyterafluoroethylene, you have minus, also known as Teflon, you have minus 97 degrees Celsius. and the melting temperature will be 327. So for these materials which have glass transition temperature as negative, then your material will be in plastic state. So your material will be in rubbery state rather than glassy state. If your material has a glass transition temperature which is in positive and higher compared to the room temperature, then your material at room temperature will be brittle. Okay, so these materials such as nylon 6s, polyester, PVC, polystyrene and polycarbonate, all these are positive glass transition temperature higher than room temperature. Next is polyethylene, which is high density. It has minus 90 degrees Celsius glass transition temperature and melting temperature is minus 137. For polypropylene, you have minus 18 degrees Celsius as the glass transition temperature and 175 as the melting temperature. For nylon 66, 57 degrees Celsius and melting temperature 265 degrees Celsius. For polyester PET, you have temperature as 69 degrees Celsius as the glass transition temperature. Okay, so for polyester PET, we have 69 degrees Celsius as glass transition temperature and 265 degrees Celsius is the melting temperature. Next is polyvinyl chloride PVC. It has 87 degrees Celsius as glass transition temperature and 212 as the melting temperature. And next is PVC 87 and 212 and polystyrene 100 and 240 degrees Celsius as melting temperature. Polycarbonate you have 150 and 265 degrees Celsius as melting temperature. Next is factors which affect glass transition temperature. TG. So the chain length Tg is the proportional to the molecular weight of the polymer. So as you keep on increasing molecular weight of the polymer, your Tg will increase. Chain stiffness. So it increases if there are double bonds, aromatic groups present in the chain. There is bulky or large side groups are present, also known as pendant groups, aromatic groups. Okay, and these increases in the glass transition temperature. Plasticizers, so this one reduces Tg. So you should remember, if you are adding plasticizers, it will be increasing plasticity and toughness of the material and also reducing Tg. Cross-linking, so if you have material highly cross-linked, it will be reducing chain mobility, so Tg will be increased. Copolymers, so Tg will be based roughly on the weight fraction of each material present in copolymer. So there will be rule of mixture. Next is effect of temperature on polymer. So as you can see, if you are increasing your material's temperature, your elastic modulus will be keep on reducing. So for 100% crystalline, your this elastic modulus will change in this way, but in other cases, having amorphous and some mixture of crystalline and amorphous region, partiality, some partial crystallinity and partial amorphous nature, then your material will behave in this particular fashion. So it won't be come out at a particular rate, but it will shift in this way. Then at particular temperature, how your elastic modulus is changing, based on that you have various regions as well. So you have glassy region, and after that you're heating, then your material will become leathery, rubbery and finally viscous before melting. So with changing cross linking as well, If you keep on increasing the cross linking, your materials, your glass transition temperature and melting temperature, it won't be changing your elastic modulus much if you're increasing cross linking. And if there is no cross linking, the decrease in elastic modulus will be very high. Here, if you keep on increasing the crystallinity, this is how your behavior of material is changing. Next is viscoelastic deformation. So in case of an amorphous polymer, it may behave like a glassy polymer at low temperatures, a rubbery solid at intermediate temperature about Tg, and a viscous liquid at the temperature is further raised. Okay, so for intermediate temperatures, the polymer is a rubbery solid showing viscoelastic behavior. So this is the behavior for load and this is behavior for strain. Okay, so if your material is totally elastic, in case of metals, you see if you're applying load at T application and T release, time of application and time of release. So you're applying load is applied and then it's released. So based on that, your strain will be at particular value of the strain, it will be contained, and then as you release the load, your strain will be again it will be diminishing. So material will regain its initial shape for elastic materials. Okay, if your material is viscoelastic, so what will happen during the application of this particular load? Your material will keep on deforming further. Okay, so it will behave as viscous material. So if you have water, if you're applying some load, it will keep on changing its particular strain. So it will behave in viscous manner. Okay, and if your material is totally viscous, then at T application it won't be showing an immediate reaction. Rather, it will be changing its strain over the time. Okay, and this strain won't be uh, changing as you release the load. It will retain in the material. So it is the total viscous type of behavior. So the combined elastic and viscous, you'll be getting viscoelastic behavior in this manner. Okay, so for intermediate temperatures, the polymer is a rubbery solid showing viscoelastic type of behavior. So here your TA is load applied time, TR is the load release time. Next is fracture in polymers. So for low fracture strength compared to metals and ceramics in case of polymers, and the fracture mode is thermosetting. In thermosetting polymers which are highly cross-linked is brittle type of fracture, and the fracture mode in thermoplastic polymers is both brittle and ductile, which are possible. Next is, in this case, crack forms at the region of localized stress concentration, and the scratches, notches, sharp flaws which are already existing, those can also act as stress raising points. Next is some factors which favor brittle type of fracture. Okay, so factors which favor brittle type of fracture. So some of the examples. So if you are reducing temperature, then your polymer will be failing in a brittle type of manner. Or you can increase the strain rate. So if you are applying your strain at very faster rates, your material is more likely to behave as the brittle nature. So it will occur in both metals as well as in polymers. Next is sharp notch presence. So if during the manufacturing or during some other application as well, if you're forming some sharp notch in your material, then this at this particular notch you'll be having high stress concentration. So if you start applying load, your material will fail catastrophically in this particular site. You can have increased specimen thickness. So for increased specimen thickness as well, your material may fracture into brittle type of nature. So these are various curves for different types of polymers. Okay, so if your material is, say, it's very soft and flexible, such as polyethylene and PTFE, you'll be having this type of curve which has very low strength but very high ductility. If your material is very brittle but it doesn't have any ductility, then it will be rigid and brittle, right? So this is melamine and phenolic. So this will be the type of curve your material will be following. So it will be having high elastic modulus but very low ductility and very high strength. If your material has intermediate strength, it has intermediate ductility, then your material will be tough and ductile. Okay, so these are the some of the examples include ABS and nylon. In case of soft and flexible, you have polyethylene and PTFE. Next is fracture in polymers. So one of the phenomena knows non-polymers is creasing. So this is the formation of these type of failure cracks. Okay, so in case of amorphous thermoplastics, below TG your material act as brittle. So at this particular temperature, you'll be having low fracture resistance. Above TG, you have ductile and high fracture resistance. And plastic yielding prior to fracture will occur. Okay, and fracture phenomena is known as creasing. Crease is known as region of localized plastic deformation, and in this case you have it form highly stressed regions associated with scratches, flows and molecular inhomogeneities, and it leads to the formation of small and interconnected microvoids. The region between microvoids is known as fibrillar bridges, and under load these fibrillar bridges they elongate and break. So this material acts as a lot of dog bone shaped type of samples that are breaking one by one in this particular direction. So there is 1, 2, 3, 4, 5 these dog bone shaped type of tensile samples that are like under the loading stage when you are loading your material in this particular way. Okay, so here also you can see it leads to the form at highly stressed regions which is associated with scratches, flows and molecular inhomogeneities, and it leads to formation of small and interconnected microvoids. Okay, and these region between microvoids, it is fibrillar bridges, and under load, the fibrillar bridges they elongate and break, and these microvoids they grow and merge. Thus, the crack propagates perpendicular to the applied tensile stress. Next is fatigue. So polymers undergo fatigue failure under cyclic loading similar to metals. Fatigue behavior is more sensitive to loading frequency than to metals. In case of high frequencies and or relatively large stresses, it can cause localized heating which softens the material leading to failure. So these are the SN curves for various materials. So in case of PET, nylon, PS and PMMA, these show better results compared to PP, PE, PTFE. These are some materials with poor fatigue performance. Next is factor affecting mechanical properties. So your first you have temperature. So an increase in temperature produces decrease in elastic modulus and also reduction in tensile strength. So factors which can affect mechanical properties. First is temperature. So if you keep on increasing temperature, it can decrease elastic modulus, first and foremost impact, which is also seen in case of metals as well. So as you can see, you keep on increasing temperature, your stress strain curve is reducing in this way. So the slope is keep on reducing. So first your elastic modulus is reducing and your tensile strength is also decreasing, right? So reduction in tensile strength but increase in ductility. You can see the fracture strain that is here along the x-axis to the final point. This is the ductility. So the ductility is increasing. Next is molecular weight. So for many polymer, tensile and impact strength increases with increasing molecular weight with the due to increase in the chain entanglements, and the viscosity also increases. Okay, so impact strength is increasing and also the tensile strength is increasing with increasing molecular weight. So here you can see the molecular weight or degree of polymerization is increasing in this way, and the mechanical properties such as tensile and impact strength is increasing proportionally, and viscosity is also increasing this way. And these are some commercial polymers that I used, which are optimized for both tensile and impact strength, which don't have very less of this as well and less of high of tensile and impact strength as well, because it will lead to deterioration in ductility. Next is factors affecting mechanical properties. Third factor is degree of crystallinity. So here higher the crystallinity, higher the close packing. So as you can see, the crystalline regions, these linear chains will come very closer, which will make density higher. So density of material will go high and close packing will be there. And these higher density, these regions will also have higher strength because of higher linking and higher resistance to both dissolution and softening by heating. These particular regions won't undergo softening as well, and it will be resistant to dissolution as well. Next is cold drawing. It is analogous to strain hardening in metals, and it is used in production of cold drawing is the uh, it is the this particular phenomena. So after yielding, your material undergoes this drawing phenomena and it is yielding, and then before fracture it is keep on elongating. So it is analogous to the strain hardening in case of metals. So in case of strain hardening, what happens? Your formation of dislocations occurs. So dislocation multiplication leads to enhancement in strength. Okay, so your material will keep on getting harder. So it is used in the production of fibers and films, and the molecular chains, they become highly oriented in this region. So you can see this is the oriented type of structure. So in this material, but in one particular direction, your material will be having high mechanical properties compared to other direction. So these molecular chains have become highly oriented. The properties of drawn materials are anisotropic. So as you can see here as well, it is perpendicular to chain alignment direction and strength is reduced. So perpendicular in this particular direction to the chain alignment, your strength is reduced. So in this direction, your material will be having very high strength, but not in this perpendicular direction. And this is what the stress strain curve for plastics polymers looks like. Okay, so there is very high ductility up to 3%. Not 3%, this is the strain. So after converting into percent, you have to multiply with 100. So yielding will be here. Then after that curve goes down, then cold drawing process will be there. So chains will keep on aligning. So that's why this at this particular place your stress will be almost constant. Okay, so that's it from lecture notes. I'll be repeating questions once again. Okay, so in a bit I'll be repeating questions once again. Okay, so first question is, which of the following types of the molecular structure present in the thermosetting polymers? Your options are linear polymer, branched polymer, cross-linked polymer and network polymers. So correct answer here will be cross-linked polymers. Okay, so in case of thermosetting polymers, they are highly cross-linked. A thermosetting polymer, often called a thermoset, is a polymer that is obtained by irreversible hardening or curing process in which a soft solid or viscous liquid pre-polymer hardening a soft solid and viscous liquid pre-polymer known as resin. So these are two types of structures. So in case of thermoplastics, there are linear type of polymers, and in case of cross-linked materials, we'll be having thermoset type of material. So because of the formation of these cross links, your material can't undergo or can be reformed. While these materials can be reheated and formed into other shapes multiple times. So these are highly recyclable. Next is, which of the following is an example of thermoplastic material? Your options are camera bodies, electric installation, electric plugs, or automobile parts. So the correct answer here will be electric installation. Okay, so explanation: bakelite and other resins such as thermosets are used for making electric plugs. And automobile parts and camera bodies, they also need to be very rigid and high temperature sustaining. So these are also made of thermosets. Next question is, which of the following monomers can be used to create a polymer through addition polymerization? Your options are ethylene, propylene, styrene, and all of the above. So the correct answer here will be all of the above. So addition polymers are formed when monomers bond to each other without the loss of any other atoms. The examples of addition polymers include polyethylene, which is made from ethylene monomers, which is used for packaging films, toys, bottles, coatings, etc. In case of polypropylene, it is made from propylene monomers, which is used for hinges, molding, rope, outdoor carpeting, etc. Polystyrene is made from styrene monomers and it is used for transparent containers, foam cups, insulation, etc. Polyvinyl chloride, it is made from vinyl chloride monomers used for pipe and tubing, raincoats, phonograph precoats, etc. Next question is, chain polymerization mechanism may occur due to. Your options are free radical, cationic, anionic, or all of the given options. So correct answer here will be all of the given options. So explanation: free radical polymerization is a type of chain growth polymerization along with anionic, cationic, and coordination polymerization. So the free radical polymerization is a polymerizing approach by which successive addition of free radicals takes place to form a polymer unit. If a sample of polystyrene has a molecular weight of 100,000 gram per mole and each repeating unit has a molecular weight of 104 gram per mole, what is the degree of polymerization of the polystyrene sample? So your options are 960, 9600, 10,000 and 100,000. So the correct option here will be 960. Okay, so here degree of polymerization can be defined as the number of repeating units in a polymer chain. So degree of polymerization can be given as Mn upon M. Mn will be the number average molecular weight. M will be the repeat unit molecular weight. So here number of atoms times the atomic weight. So here it's given 104 gram per mole for polystyrene and the number average molecular weight is given 100,000. So you just need to divide 100,000 to 104. You'll be getting 961, which is approximately equal to 960. So the first one would be the correct option. So you have joined late, so I'll restart the questions again. So first question was, which of the following types of molecular structure present in the thermosetting polymers? Your options are linear polymer, branched polymer, cross-linked polymer and network polymers. So here correct answer will be cross-linked polymers. So in case of thermosetting polymers, they are highly cross-linked. A thermosetting polymer, which is often called a thermoset, is a polymer which is obtained by irreversible hardening process, also known as curing. Okay, and these are the types of structure that are seen in thermoplastic versus thermosets. In case of thermoset, you will be having linear type of polymer chains, while in case of cross-linked polymers, you will be having these cross-linked covalent bonds between various chains, leading to only non-formable type of structure. So you can't recycle cross-linked polymers, while you can easily recycle thermoplastics. Next question is, which of the following is an example of thermoplastic material? So your options are camera bodies, electric installation, electric plug, and automobile parts. So the correct answer here will be electric installation. Because all of the other options, bakelite and other resins, thermosets are used for making electric plugs, and automobile parts and camera bodies are also need to be very rigid and high temperature sustaining. So these are made of thermosets. Next is, which of the following monomer can be used to create a polymer through addition polymerization? Your options are ethylene, propylene, styrene, or all of the above. So correct answer here will be again all of the above. Addition polymers are formed when monomers bond to each other without the loss of any other atoms. Examples of addition polymers include polyethylene, which is made from ethylene monomers, used in making packaging films, toys, bottles, and coatings. Polypropylene, it is made from propylene monomers used for making hinges, molding, rope, outdoor carpeting, etc. Polystyrene, it is made from styrene monomer and it is used for transparent containers, foam cups, insulation, etc. And then PVC, it is made from vinyl chloride monomers used for pipe and tubing, raincoats, phonograph records, etc. Next question is, chain polymerization mechanism may occur due to. Your options are free radical, cationic, anionic, or all of the given options. So correct answer will be all of the given options. So free radical polymerization is a type of chain growth polymerization along with anionic, cationic, and coordination polymerization. Free radical polymerization is a polymerizing approach by which successive addition of free radicals take place to form a polymer unit. If a sample of polystyrene has a molecular weight of 100,000 gram per mole and each repeating unit has a molecular weight of 104 gram per mole, what is the degree of polymerization of the polystyrene sample? So for polystyrene, you are given molecular weight. You are also given the polymer's molecular average weight. So for degree of polymerization, you have to just divide 100,000 with 104 and you'll be getting the correct answer at 960. Okay, so this is the definition of degree of polymerization. It can be defined as the number of repeating units in a polymer chain. So Mn upon M, Mn will be number average molecular weight and the M will be the repeating unit molecular weight. Okay, so this will be 960. Next question is again, you have to just divide 1000 with the 10. So a polymerization reaction with 10 monomer units produces a polymer with a molecular weight of the 1000 gram per mole. What is the degree of polymerization? So your option are 1, 10, 100 and 1000. So 100 will be the correct answer. Similarly to previous calculation. Next question is, the characteristics of condensation polymerization are given below. Your options are only CC linkages present in the polymer structure, use of bifunctional or polyfunctional monomers, elimination of a small byproduct molecule. So in case of condensation, you have elimination of a small byproduct molecule such as S2 or ammonia. You also have use of bifunctional or polyfunctional monomers. The only CC linkage present, so this is not correct. There can be nitrogen, oxygen also present. So the correct answer here will be 2 and 3. So this second one will be the correct option. Okay, so one of the example you can see here, the main chain is also consisting nitrogen. Okay, so structure of nylon 6,6. So besides CC linkages, polymer structure also contains atoms such as oxygen, nitrogen, etc. at regular intervals in the main chain. Which of the following polymer type is not classified on the basis of its application and properties? Your options are rubbers, plastics, fibers and synthetic. So out of these, initial three are based on applications. This one is based on origin. Okay, so synthetic polymers are classified on the basis of the origin of polymers, and these are known as man-made polymers. There are two types of polymers, synthetic and natural. Synthetic polymers are derived from petroleum oil and made by scientists and engineers. Examples of synthetic polymers include nylon, polyethylene, polyester, Teflon and epoxy. Natural polymers occur in nature and can be extracted. Which of the following is a thermostatic polymer? So your options are polystyrene, polyolefins, nylon, phenolic resins. So the correct answer here will be the last one. This is the only thermosetting polymer here. Others are thermoplastics. So phenolic resins falls under the plan of thermosetting polymers, and rest are the thermoplastic polymers which can be softened repeatedly on the application of heat. Next is polystyrene is a blank polymer. Your options are linear, branched, cross-linked and network. So polystyrene is the addition type of polymer with linear type of structure. Which polymer is an example of branched polymer? Your options are high density polyethylene, low density polyethylene, polyurethanes and nylon. So branched polymers, you can see their structures here. So these branches, they always make your material less dense compared to linear type of structures, where these chains can come very close and this structure will be highly dense. So here, as it's shown, low density polyethylene will be the one with the branched polymers. Which one is a characteristic of thermoset polymer? So your options are ductile. So thermosets are not ductile, they are highly brittle, and there are creep prone. No, they are not creep prone. Compared to thermoplastics, thermoset are not creep prone. They can sustain high surface temperatures. They are recyclable. So they are not recyclable as well. So thermoplastics are recyclable because they can be reheated and formed into other shapes, and for non-post formable. So if you form your thermoset once, if you reheat it again, it's more likely to burn and it can't be formed into another shape. Next question is, which statement is incorrect? So your options are cross-linking restricts the molecular motion, cross-linking makes polymer insoluble, cross-linking reduces chain mobility, or Cross-linking reduces glass transition temperature. So out of these, only incorrect statement is the last one. So cross-linking will be restricting the molecular motion. This is correct. So here also you can see after cross-linking, these chains movement will become restricted. And this cross-linked will make this particular structure less dense. And other options are it restricts molecular motion, which is a correct statement. Cross-linking makes polymer insoluble. This is also correct. And it also reduces chain mobility. So this is only incorrect because cross-linking will increase glass transition temperature. With cross-linking, what happens in your material? That it will become brittle. So the range for the material to be glassy, in the range it will increase. So it will only increase if your glass transition temperature is increasing. Okay, so if it is increasing up to higher temperatures, then your material will remain glassy or brittle at the temperature which is lower than that transition temperature. So this range will increase. Next question is, what is increased in a material on the addition of plasticizers? Your options are plasticity and fluidity, glass transition temperature, hardness and stiffness. So correct answer here will be plasticity and fluidity. So plasticizers are added in polymers to increase toughness and plasticity of material. So with addition, your plasticity and fluidity will increase, hardness, stiffness will reduce, glass transition temperature will also reduce. Because if this temperature is reducing, then your material will be plastic in higher range of temperature. Next, we went through some lecture notes. So firstly, there was classification for polymers. So based on molecular structure, there are 4 types. So as we can see further, based on origin, there are natural polymers and synthetic polymers. Then based on molecular structure, you can see they can be single chains. So these are linear type of structures. So there are linear. Then you have branch type of structures, side branches which are connected to the main ones. It is more soluble and fusible, and low density polyethylene is one of the example. For linear, between two chains there can be weak van der Waals or hydrogen bonding. These are soluble and fusible. Examples include high density polyethylene, polyvinyl chloride, polystyrene, nylon and polymethyl methacrylate. Then cross-link type of polymers. In this case, they're adjacent linear chains. They are joined one to another at various positions by covalent bonds. And these are insoluble and infusible in nature. And in case of network type of polymers, these are highly cross-linked and have 3D type of network. These are also insoluble and infusible. Some of the examples include rubber, polyurethanes and phenol formaldehyde. Next is classification based on thermophysical property. So in case of thermoplastics, you have heat sensitive, which soften and flow upon heating. So you can keep on reheating your material and you can soften it and you can provide a different shape to your material. It remains soluble and fusible under many cycles of heating and cooling, thus they are recyclable. And the most linear polymers and those having some branch structure with flexible chains are thermoplastics. The individual polymer molecules are held together by weak secondary forces, van der Waals forces or hydrogen bonds or dipole-dipole interaction. And they are easy to repair by welding and solvent bonding, etc. They have unlimited shelf life and they won't undergo polymerization during storage or in processing unit. Some of the disadvantages include they are prone to creep. So at higher temperatures, because of as you saw earlier, there are no branches or these type of networks, as you saw earlier, right? There are no such cross linking which will be making this movement of chains restricted. That's why these are prone to creep. These structures are prone to creep. Okay, and examples are given here. Then you had thermoset polymers, which are network polymers, and these are creep resistant and less sensitive to temperature. They can attain permanent hardness due to cross linking and then do not soften and flow upon heating. And that's why these are non-post formable, which are obtained in a soluble or fusible stage in the early or intermediate stage. But once they get cured, they will be infusible and insoluble. And these are excellent thermal and chemically stable once polymerized. Disadvantage include they are brittle and non-recyclable. Examples are bakelite, epoxy, and urethanes. Next was the curing of thermosets. So it is the process of transforming thermoset resin, which is soft, solid, or viscous state, into an infusible, insoluble polymer network under heat and pressure. The viscosity of the system rises until gelation occurs. And at this point, two phases exist, a gel phase and a sol phase. The gel phase is in the gel part and the sol phase can be extracted with solvents. The amount of sol phase present decreases as the reaction progresses further. Upon further reaction, vitrification, also known as hardening, occurs. Next is addition polymerization reaction. So here monomer units are attached one at a time in a chain-like fashion to form a linear macromolecule characterized by the presence of a few active sites which react and propagate through a sea of monomers. It is used for synthesis of thermoplastics, initiator decomposition, chain initiation, chain propagation, and chain termination. Then you have condensation polymerization reaction, which involves more than one monomer species. Monomer can react with any nearby monomer and no special activation is needed to allow a monomer to react. Here a small molecular weight byproduct such as water that is eliminated or condensed. These are the steps given here. Next is advanced polymers. So in this case you have ultra high molecular weight polyethylene. And next we had liquid crystal polymers. Based on applications, you have types of polymers. So it can be in film form. So polymeric films having thickness between 0.025 to 0.125 mm are used. And these have important properties such as low density, high degree of flexibility, high tensile and tear strength, and resistance to moisture and other chemicals. Examples: polyethylene, polypropylene, and cellophane. In case of foams, it contain a relatively high volume percentage of small pores and trapped gas bubbles. It is commonly used as cushions in automobiles and furniture as well as in packaging and thermal insulation. Next is coatings. So ingredients and coating materials are usually organic polymers which are classified as paint, varnish, enamel, lacquer and shellac. It is applied to surface of materials to protect items against corrosive and deteriorative reactions, to provide electrical insulation, and to improve the object's appearance. Next is fiber. These are the long filaments having at least 100:1 length diameter ratio subjected to mechanical deformations. such as stretching, twisting, shearing, and abrasion. It is widely used in textile industry for being woven into fabric or cloth. Adhesives, which are used to join a large variety of materials such as ceramics, polymers, and composites. Their advantages include lighter weight, ability to join dissimilar materials and thin components, better fatigue resistance, low manufacturing costs. Limitation include they can't be used at high temperatures. Some of the adhesive examples are given and applications as well. Next is elastomers. So in this case, amorphous polymer with viscoelasticity, showing viscosity and elasticity both, with very weak intermolecular forces, low Young's modulus, and high failure strength compared with other materials. For a polymer to be an elastomer, it must not easily crystallize. The molecular chain should remain naturally coiled in the unstressed state. The chain bond rotation must be free to readily respond to an applied force. And their delayed plastic deformation and examples are given, and some applications are also given. Plastics are malleable and they can be molded into solid objects of diverse shapes. Some plastics are very rigid and brittle, and others are flexible. These are used in general purpose applications and may be either thermoplastic or thermosetting. Some of the applications of plastics are given. Then these are the definitions of molecular weight. It can be number average or weighted average molecular weight. Then degree of polymerization. You have various questions based on this. So you should remember this particular formula, and based on that you can easily remember the definition as well. So as you keep on increasing the degree of polymerization, your material's melting temperature will increase. Then we had polydispersity index, which is just the uh, ratio of the weighted average molecular weight to the number average molecular weight. Then you have copolymers. So when there is more than one type of mer present, the molecule is a copolymer. The copolymers are common type of material used commercially. So some of the examples are ABS, polyethylene vinyl acetate, nitrile rubber, etc. And these are created with the various types of monomers, and it is frequently used to enhance or change particular characteristics of plastic. Some types of copolymers include graft copolymers, block copolymers, and alternating copolymers. Physical state of polymers. So classification. So it can be partially crystalline state, it can be viscoelastic state, it can be highly elastic state such as rubbers, and also glassy state where organic glasses from polystyrene, polymethyl methacrylate, and polyvinyl chloride are some of the examples. So material can never, your polymers can never be 100% crystalline. There will always be some portion in the crystalline form and some portion in amorphous. Next is crystallinity. So there can be crystalline or ordered structures in your polymers as well. So material can be up to 95% crystalline but never 100% crystalline. And these crystalline regions, they make your material's melting temperature more sharp, and they give properties. Okay, and these are the some orderly arrangements of molecular chains, and highly crystalline means higher density, more strength, and higher resistance to both dissolution and softening by the heating. So that's it from my side. Thank you.